Backbreak can happen for a lot of different reasons. We typically have three major events that occur, though. The first is over-confinement of the shot. The second is we have cratering occurring, which will almost always cause backbreak. We could see in that crater profile, just the general procedure and mechanism of it, it's going to cause backbreak to occur because it breaks in a 360-degree arc. The last one is gas injection into soft seams, meaning we have a soft seam of rock, we have mud, we have a cave, we have something that's much softer than the rest of the rock, and the gases from the explosive will move in there, and it pops that seam open, which can cause a backbreak to occur. Now, gas injection, we can typically handle that through stemming or decking through soft seams and by avoiding overloading. So in order to treat backbreak, what we're going to talk about here is dealing with over-confinement of the blast using what we call the 4D energy principle, or the 4D approach to blasting. And to do this, we need to take into account both the confinement, the complete confinement, including both the burden and the timing of the blast. Here's an example. This is mine that we were working with. And because of COVID, we were actually not able to travel to the site at the time that we were working on it. And so what we did was we used Straios. We had an on-site team come in that was local to the area. They could fly a drone and get us our profiles. And we were told, the profiles were nice and smooth, and there was no real concerns for backbreak or large tows. And this is what we actually got. Now, this blast was being designed for a 12-foot burden. So you can see here we had 12 feet of burden at 6 feet from the top of the hole. By the time we got to 32 feet down, we had 32 feet of burden. You can see we had major backbreak occurring here, and that was leading to a very large tow burden, which gave us large potential over-confinement problems. Now, in terms of designing burden, designing the base simple burden is relatively easy. There's a lot of different ways to do it. There's the general rules of thumb. There's the Konya burden formula that people use. But in the end, that's sort of the easy part. The difficult part is that we normally don't get to apply our perfect design burden because we have real field conditions, for example, such as tow burdens. And so we need to, first off, be able to correct potential problems with tow burdens. And in eliminating that backbreak, or in solving some of those backbreak problems, we can actually start to address that and smooth this face up so we have very minimal, if any, real tow burdens. You can see in this case, even if we came and put the hole right on the crest, we would have still had, let's say this is 6 feet here, maybe this is 4 feet. We would have still had 28 feet of burden on a hole that should only have about 12 feet to 13 feet of burden at the maximum. And so in this case, we can't necessarily use our normal design approaches here. Now, we can use a lot of different tools, such as pre and post blast cross sections to help identify the extent of backbreak. And this is just an example from a Straios project. And you can see here, we can look at where the holes are. We can line up the cross sections of the actual original bench and then the post-blast profile. And we can see then by lining up where our last set of holes was with the cross section, the potential extent of the backbreak from each shot. Now, while we need to deal with tow burdens, and there's a lot of ways to do that, we can use a trim shot, we can use angled holes, we can change the timing to shoot it in a different way. We have a lot of tools at our disposal, and we can typically find ways to deal with these different tow burdens. However, there's one thing that we still have to address, and that is improper timing that results in a large burden or an over-confined situation.